Okay, so our next speaker is Homayun Karimi from McMaster, and he's going to talk about Gordon-Litherland pairing for links in surfaces and applications to alternating links and concordance. Please.
Thank you. Thank you for invitation and introduction. Just a second. Okay, so this talk is based on 3 joint papers. One is with Hans Boden and Michael Chrisman. You can see the archive address for the paper. And the other 2 are 2 joint works, both of them with Hans Boden, and one of them is on archive. You can see the address, and the other one is still work in progress. So let me start with definition of the signature. So for classical knot, this goes back to Trotter and Murasugi. So if you have a knot K, and if you take F to be the Seifert surface for K, then you define the Seifert matrix. It's an n by n matrix, and the entries of this matrix are defined to be, you take the basis alpha 1 up to alpha n for the first homology of the surface F, and you take the linking number of each alpha I with the push off of alpha j. And that determines an n by n matrix for us. And now we can make this matrix symmetric by adding the transpose of this matrix. And then because that's a symmetric matrix, it has real eigenvalues and it has signature, and you define the signature of the knot K to be the signature of this matrix. Then in 1978, Gordon and Litherland had another approach to find the signature. They took a spanning surface for K, and by a spanning surface, we mean a surface not necessarily orientable, which has the knot K as its boundary. And then we take a tubular neighborhood N of the surface, and you look at the double cover of this surface F, which is the boundary of the tubular neighborhood, and they look at the projection from the double cover of F to F. And now you can define the transfer map, which is a map from the first homology of the surface into the first homology of the double cover. And you take a homology class A, you look at the inverse image of A under pi, and you take the homology class. This is called transfer map. Now, using this, we can define a bilinear form, G sub F. It is defined on the first homology of F, and it takes 2 homology classes alpha and beta. You take the transfer map, apply it on alpha, and you take the linking number of the result with the beta. So this defined a bilinear form for us, and also define the normal Euler number of F to be minus the linking number of the knot K with a parallel K prime, which is a push-off, which misses F. Now with these 2 things in hand, Gordon and Litherland proved that for any spanning surface F for a knot K, G sub F is a symmetric bilinear pairing. And if you take this signature of that pairing and add this correction term, add this E of F, which was minus the linking number of K with K prime, divided by 2, that is exactly the signature of the knot. And it worth noticing that if you started with a Seifert surface with F, which is orientable, then the correction term is 0, and this matrix of G sub F coincides with the symmetrized Seifert pairing. So in a sense, it generalizes that pairing and calculates signature for us. Any questions so far? Now, we want to generalize this work into the setting of knots inside surfaces. So we start with the surface sigma, which is a compact, connected, and oriented surface. And we want to define this GL pairing for knots inside sigma cross I. And as a result, we can define signature, determinant, and nullity for these knots. And after doing that, we will have several applications for that. And all these results hold for links, even if I state it for knots, unless otherwise stated. So before we define the Gordon-Litherland pairing, we need the notion of linking inside sigma cross I. So if you have two disjoint knots J and K inside sigma cross I, we define the relative linking number denoted by this notation, linking sub sigma of J and K. And we define it as usual. We take J and we take a two chain B, which bounds K, and we take the intersection number of J and B, and this B is a relative two chain, meaning that if you look at sigma cross I, so B is something that has K as a boundary on one side, and on the other side of the boundary, it comes to sigma cross 1. Now, so that's the definition of the linking number, and diagrammatically, this calculates when you take the number of times that the knot J goes over K, and you count that with sign. So you can look at this picture and you can see several calculations of the linking number. For example, I highlight this one. If you look at J and L, so J and L are disjoint knots inside the surface, and you see that J goes over L only once with negative sign. So the linking number is -1. So now we have the notion of linking. So using that, we define the Gordon-Litherland pairing as follows. So we start with a knot K, and we take a spanning surface F. Remember, it's a surface with boundary K. And we define the Gordon-Litherland pairing, which is defined on the first homology of F. If you take alpha and beta, two homology classes inside F, you take the linking number of the transfer map over alpha with beta, and then you change the order of alpha and beta, you add these two together and divide it by 2. So first thing that you can show is that the Gordon-Litherland pairing of alpha and beta, if you change so it's linking of tau alpha and beta minus this quantity, which is the intersection. P is the projection from sigma cross I to sigma. If you look at alpha inside here and project it down to sigma and do the same for beta, on sigma you can look at the intersection number, and you need to subtract this from the linking number. That gives you the pairing. So these two formulas shows that the first one shows that this pairing is symmetric. The second one shows that this pairing is integral. So we have an integral symmetric pairing defined on the first homology of F, which is the spanning surface for the knot K. So, and then we define the signature as follows. So starting with the knot K inside sigma cross I with the spanning surface F, signature is defined to be a signature of the symmetric pairing that we defined in the previous slide, plus a correction term, which is 1/2 E of F, and E of F is defined to be minus the linking number of K with K prime, which K prime is the longitude of K, which misses F. Now, the first question is, in what sense this signature is an invariant for the knot K? So to answer this question, we define the notion of SSR equivalence. So between two spanning surfaces, they call SSR equivalent if you can go from one to the other by a combination of these following moves. So the first move is ambient isotopy. The second one is attaching or removing a one handle. By one handle, I mean something like this. And the last move is attach or remove a half-twisted band as depicted in this picture. So if you can go from one surface to the other by a sequence of these moves, they call SSR equivalent. Now, the first thing that you can show is that if you have two surfaces F1 and F2, and they are SSR equivalent spanning surfaces, then this quantity that we define, signature plus the correction term, is equal for both of them. So as a corollary, if F is a spanning surface for a knot K, then this signature that we define, namely signature of the Gordon-Litherland pairing plus the correction term, depends only on the SSR equivalence class for F. And now we can also define other invariants such as determinant and nullity. The definition is as usual. So determinant of the knot K with respect to spanning surface F is absolute value of the determinant of the matrix GF, the Gordon-Litherland matrix, and the nullity of the knot K is also defined to be the nullity of that matrix. Again, we can ask in what sense these are invariants for the knot K. So again, we have a theorem. It says that if you have two surfaces, F1 and F2, and they are SSR equivalent spanning surfaces for a knot K, then the determinant of K using either one of the surfaces are equal. Also, the nullity of the knot K using either one of these surfaces are equal. So they are invariants for the knot up to SSR equivalence. Now, these are some facts about SSR equivalence. So first of all, for classical knots, every classical knot admits the spanning surface. These are well-known facts. And also any two spanning surfaces for a classical knot are SSR equivalent. But both of these facts fail for knots and thickened surfaces, i.e. you can have knots which doesn't admit any spanning surface. And also you can have more than one SSR equivalence classes for a given knot K. So the proposition that we have here is that if you start with a knot K in a thickened surface sigma cross I, then the following are equivalent. So K is the boundary of a spanning surface F if and only if the homology class of K vanishes in the first homology of sigma cross I with Z2 coefficients. And if either one of these holds, then K admits a checkerboard coloring. And it's worth noting that, so either we have no spanning surface or exactly two spanning surfaces. So these two happens when the genus of sigma is bigger than 0. So here is the lemma that shows how we deduce the uniqueness of the spanning surfaces. So if you start with a knot K and assume it's checkerboard colorable, meaning that it admits a spanning surface, and assume the genus of the sigma, the surface sigma is positive, then two spanning surfaces F1 and F2 are SSR equivalent if and only if they represent the same homology class in the second homology of sigma cross I relative to K with Z2 coefficients. So as a corollary, any spanning surface is SSR equivalent to either black or white surface. And you can also show that the black and white surface are not SSR equivalent. So the black and white surface are the two non-equivalent spanning surfaces for the knot K. So that means the signature that we define typically comes in pairs. So for each knot, we have a pair of signatures, also a pair of nullity and a pair of determinants. So these invariants comes in pair. Now that we had the definition for the Gordon-Litherland pairing, we can use them to get some applications. So I'm going to list the 3 applications today. The first one is the application of this pairing to the case of alternating knots inside thickened surfaces. So let me review what we know in the classical case. So for classical knots, this question goes back to Fox, and he has a famous question. He asks, what is an alternating link? Which means that can we characterize alternating links geometrically? And in 2017, Josh Green and Josh Howie independently answered this question. In fact, you can see the theorem of Josh Green here. So Green proved that if you have a link L, it is alternating if and only if it bounds a positive and definite, a positive definite and a negative definite spanning surfaces. And positive definite with respect to Gordon and Litherland pairing means that, remember, we had a symmetric pairing. So a spanning surface is called positive definite if the Gordon-Litherland pairing is positive definite. And actually, Green proved his theorem in a more general setting, namely for links inside Z2 homology spheres. So he proved that inside Z2 homology sphere, if a link bounds a positive definite and a negative definite spanning surface, then that link, first of all, should be classical and it should admit a alternating diagram. So the goal here is to extend Green and Josh Howie's result to more general pre-manifolds, namely thickened surfaces. So it's a good point to remind ourselves what we mean by alternating links. So here is a definition. A link diagram D on a surface sigma is called alternating if when you travel along each component of the link, the crossings alternates between overcrossing and undercrossing. And when a link L admits one alternating diagram, then that link is called alternating. And here is another notion. So something is called cellularly embedded. When you look at the diagram D inside sigma, and you look at sigma minus D, it should be union of disks. In this case, D is called cellularly embedded. And a remark here is that if your diagram is cellularly embedded and it is alternating, then it is checkerboard colorable. So that's the relationship between being alternating node and being checkerboard colorable. And here is a picture of an alternating link. So before I explain the theorem about how we characterize alternating links inside thickened surfaces, I just need a couple definitions. So the first thing is with regard to the checkerboard coloring. So when you have a diagram on a surface and assume it is checkerboard colorable and checkerboard color that diagram, then if your crossing looks like this, then it's called type A. And if your crossing looks like this right picture, it's called type B. And based on that, we can define an incidence number. So incidence number of a crossing is 1 if that crossing is of type A. And it is -1 if that crossing is of type B. We also have other notions. We have type 1 crossings. This is only defined when you have a checkerboard coloring and your diagram is oriented. And in that case, if the picture looks like the top left, then it's called a type 1 crossing. And if it looks like the top right picture, it's called type 2. So that's the definition of type and the incidence number for a crossing. Now if you start with the coloring, so if you checkerboard color your diagram, then you get 2 spanning surfaces. So one is the black surface coming from you take all the black regions and put them together. And when you get to a crossing, you put a half twisted band. So that's the spanning surface for your knot. The other spanning surface is the white surface, using the same thing, but this time using white regions. So for these particular spanning surfaces, if you add all the negative of all the incidence number over all the crossing which are type 1 and call it mu, and do the same thing for the black surface and take the sum over the incidence number of all the crossings which are type 2, then you can show that this mu for the white surface is -1/2 of the correction term that we had before, also for the black surface. Then here is a definition of a positive definite spanning surface. So a spanning surface is called positive definite if it's Gordon-Litherland is positive definite, and also it's negative definite if it's Gordon-Litherland pairing is negative definite. So the lemma that you can have here is if D is a link diagram, which is cellularly embedded, remember that means the complement of the diagram is only disks, and assume this diagram is alternating, then the black and white surfaces are definite surfaces, and one is positive, the other one is negative. So the idea of the proof is that when you look at the Gordon-Litherland pairing of a surface, let's say B, the black surface, then because the diagram is alternating, all these crossings have the same type. So they all have incidence number -1. And as a result, the Gordon-Litherland of each individual gamma with itself is sum over the incidence number when that gamma passes through the crossings. So you add a bunch of negative numbers together, you get a negative numbers. That means this form on each gamma is a negative, so that means that surface is negative definite. So you can use the same argument to show the other surfaces positive definite. Now, the proposition that we have here is if D is a connected checkerboard colorable link diagram on a surface and assume it is cellularly embedded, then this diagram is alternating if and only if the black and white surfaces are definite of opposite signs. So this is the first step. So this proposition characterizes the alternating diagrams. So the next step would be to characterize the alternating links, but the first step that we need is to characterize the alternating diagrams. This proposition does that. And one direction is the lemma that you saw in the previous slide. And the other direction is that assume the black and white surface are definite, and one is positive definite and one is negative definite. If you look at the difference between signatures, so because say this one is positive definite, you get B1 of W, the entire rank of the first homology as a signature, and the other one is negative, so you get negative of B1. So the difference between signatures is adding the first Betty number of the two surfaces. And then you do a bit of work by analyzing the correction terms. And if you do that, you realize that all the crossings should have the same type, either type A or type B. And that's an easy exercise to see that when all the crossings have the same type, then the diagram should be alternating because, for example, if you have a diagram like this, which is not alternating, then if you start to checkerboard color this diagram, you can realize that this one has eta equals to -1, this one has eta equals to +1. So they have different incidence numbers. But this doesn't happen in this case because all the incidence number, you can show that they are equal. As a result, the diagram should be alternating. Okay, now we start with a link. So the next step to characterize alternating links. So we start with the link, which is start with a non-split link, and assume it has minimal genus. So you don't need to worry about this assumption now, because later on we prove that you can remove this hypothesis. So I'm not going to even define it here. I define it later. So you start with a link, then you can prove that that thing is alternating if and only if you can find a positive definite and a negative definite spanning surface for that link L. So I'm going to sketch the proof here. So if the surface sigma has genus 0, means that we are in the case of the classical links. So that's Josh Green and Josh Howard's result. So you can assume that the surface sigma has genus bigger than 0. And one direction is that if you start with an alternating link, then we saw in the previous slides that that means it admits an alternating diagram. And once you have an alternating diagram, you can take the black surface and the white surface. Those are two spanning surfaces for this link L, and they are definite and of opposite side. So that's the proof in one direction. So the other direction, the non-trivial direction, is that assume now that you have two spanning surfaces. They are definite of opposite sign, but you want to show that the link is alternating. So first of all, you need to assume a technical thing that I'm not going to talk about it here. So you can assume these two surfaces don't intersect in any simple closed curve. Because if they do, then we have a proposition that it says that you can remove those intersections and still get spanning surfaces, definite spanning surfaces with opposite side. So let's assume that you have two spanning surfaces and they don't have simple closed curve in their intersection. So here is a picture. So this blue arcs means that my link L, and this dashed red and green are two spanning surfaces for my knot K. Oh, sorry, for my link L. Now, you can intersect these two. You can see that these two surfaces intersect each other. So I put them in two separate pictures, but if you look at them once in one picture, namely here, you can see that they have one arc of intersection. So two spanning surfaces for the knot L, they have a finite number of arcs of intersections. Now, the thing that we do is that you collapse these intersections to a point and look at the union of these two spanning surfaces, and inside that union, you collapse those arcs of intersection. You can prove that the result is another surface S, and you can prove that this surface has the same genus as the surface sigma that we started with. Now my link L lives inside a tubular neighborhood of the surface, namely S cross I. Then you need to do some magic, use some classical theorems to show that this link L inside S cross I is the same as L inside sigma cross I. So you need to show that these two links are the same. Once you do that, then the two spanning surfaces P and N that you started with are the checkerboard surfaces inside this new surface. And you can see that now you have two checkerboard surfaces which have the opposite sign, and both of them are definite. And then use the previous proposition to show that in that case, L must admit an alternating diagram. So you can prove this theorem in this way. Okay. So that was the first application, and I'm going to quickly outline the two other applications. So the second application is application for the so-called virtual concordance. Here is a definition. So if you have a knot K0 inside sigma 0 cross I, another knot inside sigma 1 cross I. So here is a picture. So you have a I guess it's difficult to have a picture. So here is sigma 0. So my knot K0 lives here. And here is another surface, sigma 1 cross I. My knot K1 lives here. If you can find a three-manifold W with boundary these two surfaces, so that's my W, and then cross it with I. So this whole picture is W cross I. And inside this, if you can find an annulus that connects K0 to K1, then K0 is called concordant to K1. In particular, K is called a slice if you can find a three-manifold W with boundary sigma such that inside W cross I, K bounds a disk. Now, the theorem that we proved here is if you start with a knot K, which is virtually a slice, and assume it has a spanning surface F, then the signature of this knot should be less than or equal to nullity, and the determinant should be a perfect square. You can compare this result with the classical results. So remember, in the classical results, if a knot K is a slice, then its signature vanishes. So here, if you start with a knot K, which is a slice, with nullity 0, then you can show that the signature vanishes. If the nullity is not 0, then it's an upper bound for your signature. So there is a key step in proving this theorem, and the key step is the existence. It's an existent result using obstruction theory, which is closely related to Pontryagin-Thom construction. And here is an outline of the thing that we needed and we proved here. So if D inside W cross I is a slice disk for a knot K, and F is a spanning surface, you can put this F and D together. You get a closed surface E. And the question is, under what condition this surface E inside W cross I bounds a three-manifold V? So if such a three-manifold V exists, then you can prove this result. So the first step is to show such a manifold exists. And here is the result that we have. So first of all, if you start with a non-orientable surface, that's the connected sum of RP2s. And if you look at the Euler, if you look at the tubular neighborhood of E, and let E be the Euler number, which is the self-intersection of F inside the tubular neighborhood, then the necessary condition that you should have in order for E to bound the three-manifold, first, you should have the Euler class of E should vanish. And also E should represent the zero homology class inside W cross I with Z2 coefficients. Those are necessary conditions if you have a three-manifold V which bounds E. And what we proved here is that these two conditions are sufficient as well. So as long as you have these two conditions, then you can find the three-manifold V which bounds A. Once you have this result, then you can prove the previous result about signature of slice knots. Okay, and that was the second application. And the last application I'm going to quickly talk about is the application to virtual knots. So a virtual knot is a virtual diagram is embedding of S1 inside R2, which just like the classical diagrams, it has over and under crossing, but in addition, it might also have another type of double points, which we call it virtual, indicated by a small circle around the double point. So, and this diagram means that you have a knot inside a thickened surface, something like that goes around like this. Instead of projecting this knot on sigma, if you project it onto R2, the diagram that you get is a virtual diagram. And whenever you have this virtual crossing, means that one strand of the knot goes in one side of the surface and the other strand goes under that sheet inside the surface. Anyway, now you can relate the virtual knot to knots and surfaces as follows. You can say that a knot inside a sigma cross I. You can say that there is a one-to-one correspondence between virtual knots and knots and surfaces up to a move so-called stabilization, which means that you have a knot inside the surface, you have a knot K, and you just add another handle to this surface. So you increase the genus of the surface. This is called a stabilization. If you look at the set of knots under this move, then that's in the one-to-one correspondence between virtual knot diagrams. And then you can talk about, now that you have several different surfaces that you can put your knots inside those surfaces, you can take the minimum among all those surfaces and define the minimal genus of a knot to be that minimum genus, that you can realize your knot inside that surface. So Cooperberg showed that if you start with any stable equivalence class of a knot, it has a unique minimal genus representative, and uniqueness is up to diffeomorphism of the pair sigma cross I and sigma cross 0. And we had this definition before. A diagram is called cellularly embedded if the complement of the diagram is disks. So the theorem that we have here is that if you start with the diagram D, which is cellularly embedded and checkerboard colorable, remember in this case we have two spanning surfaces for the knot. So we have a pair of determinants. If both of them are non-zero, then the knot K has minimal genus. And that was my last application. And here is some problems for future research. So the first problem is what you can say about the links. So that concordance result that we had is only for knots. So can you say something about links, i.e., is it true that if you start with the link L, which is virtually a slice, can you prove that the signature is bounded by nullity and the determinant is a perfect square? So we had this theorem for knots. Can you generalize it for links? The second problem is for virtual links, to what extent nullity and nullities are concordance invariant. So notice that for classical links, nullity is a concordance invariant. So if two links are concordant, their nullities are equal. For a reference, see a paper by Kaufman and Taylor from 1976 called Signature of Links. And the last question here is, if you look at Gordon and Litherland paper, so they start with a K, they take a spanning surface F, and so this spanning surface F, you can push this inside before. So here is a picture. So I have before, the boundary is S3. My knot K lives inside S3, and there is a spanning surface F bounding this knot. Push the interior of the surface inside before. Now you can look at the double branch cover of before over this F. You can and call this double branch cover M sub F. Now, one thing that Gordon and Litherland show in their paper is that if you look at the signature of this four manifold, the signature of this four manifold is the same as the signature of the Gordon-Litherland pairing. And then they add this correction term, 1/2 of E of F1, and they prove this theorem that the signature plus adding this correction term is independent of choosing the spanning surface. But their proof is based on G signature theorem. So the question is, can you use that approach in this setting too? So can you use something like G signature theorem to prove this theorem in this setting as well? So these are all the things I wanted to say today, and thank you for your attention.
Okay, thank you. Thank you very much. So,
you're welcome.
So everybody, if you have questions, then you are free to unmute yourself. Okay.
Hi.
Hi.
Hi. Do you think is it possible to prove writing conjecture in your version?
I'm sorry, what conjecture?
Writing conjecture. For alternating link, different diagrams, different minimal diagrams are related by finite sequence of writing. In today's version, how do you think about surface cross as sigma version?
I'm sorry. I guess I couldn't understand your question. You are talking about the
do you know Menascu-Thistlethwaite splitting theorem?
Yes.
So this is what he's talking about. So he's asking whether there is some way to prove something similar for alternating diagrams on higher genus surfaces.
Yes, and we did that, and it's a different paper. So you can look at one of our paper. It's called the Jones-Kruskal polynomial, and I guess I don't remember the name. Sorry, it's a start with Jones-Kruskal. So it's a paper with me and Dr. Gordon. So we proved that for alternating links admits minimal crossing diagrams. So the alternating diagrams have minimal crossings. I hope that was you were asking.
No, I don't think so. He's asking about the flighting conjecture, not about.
Oh, flighting. Sorry. I'm so sorry. Flighting.
Yes.
For sigma, when the genus
Yes.
bigger than 0 is still open.
Yeah. Thank you.
You're welcome. Sorry about it.
Okay. Okay, so if there are no further questions, then let's thank the speaker again. Thank you very much, Homayun.
You're welcome.